a very good morning to all of you and to welcome you to this session this morning. Our presenters today are Mr. Ayman Tallouni, who is a program officer at the United Nations Environmental Program, UNEP, known as UNEP, as well as a regional office working for Regional Office for West Asia. Following Mr. Ayman, Mr. Bassam Al-Assad will add to the presentation of Mr. Ayman, and who is a consultant to UNEP UNIDO High Ambient Project, and will be wrapped up and add to the information by Dr. Walid Shakroun, coming over from the University of Kuwait, Kuwait University, who is also a fellow of ASHRAE, and been also, all of the three gentlemen been working on this particular subject since a few years back. So it's to introduce Mr. Ayman Tallouni first, and hopefully as the title states, it's a challenges in identifying low GWP refrigerants for high ambient temperature climates. As you may be aware, new refrigerants are developed, not taking into consideration collection of reaction of using these particular refrigerants in high ambient. So I hope today we'll be having a good input about this from the three gentlemen. Mr. Ayman, please go ahead.
Thank you, Samir. Good morning, everyone, and season greetings for those who are celebrating the Eid tomorrow. Thank you so much for being that early here with us today. I would like to start by thanking the AUP and ASHRAE for the very kind invitation. I'm really humbled to be here today. Enjoyed being at the AUP and always enjoyed cooperating with the ASHRAE and AUP colleagues. Yeah, okay. Is it clear now? Okay, thank you. We're going to speak today about, I think, a topic which is not new to you, but we're going to try to handle it and address it from a different perspective and angle related to the considerations associated with the issues to the high ambient countries. I know that Lebanon is not an high ambient countries, but it is part of a region that is suffering of this high ambient characteristics, and its markets affected more or less by what's going on in the region, because it's going to affect eventually the technology selection at the end. So I didn't want to have the full 1 hour presentation that you are looking to me only, so I asked the gentlemen with me, Dr. Shakroun and Mr. Bassam Al-Assad, who are really an excellent and fine expert working with us in this project since a few years, to share me in presenting the key objectives and outline of this project, aiming at trying to explain to you, and you can benefit out of this. As you will see, it's not only about the high ambient. You can use the same approach for your country as well, as an approach to assess the long-term alternatives and being part of the decision-making for selecting the refrigerant, and not only receiving what is available commercially by the technology providers. In order to do so, we will be doing the presentation into 3 segments. I will be addressing during the first part of it, the presentation, 2 key issues: the driving forces behind this topic and initiative, and the global and regional relative initiatives to assess the future refrigerants. Well, while Dr. Shakroun will be following me and describing in a little bit in details about the characteristics of this relevant research, which is called BRAHA. This BRAHA stands for the Promoting Low GWP Alternatives for High Ambient Countries. And then just we put the acronym BRAHA to simplify the case instead of repeating this long name every time. And then he will be also throwing some light on and shed on the project of AHRI. It's a global well-known project with the same purpose as well, and explaining the differences between the 2 projects. The third part will be handled by Dr. Bassam, Mr. Bassam, which is about other relevant research under the BRAHA project related to the district cooling, and he is going to explain why we are concerned about district cooling and what's its relation with this high ambient issue. Then we'll try to have some concluding message and discussion points for you to help us in trying to shape up some key recommendations out of this session. So without further explanation about what we are going to present, I will start by my part, which is going to to comprises of the driving forces. We're going to speak about the policy background, the global outlook of the refrigerant industry and air conditioning industry, including the policies everywhere in the world currently, the major air conditioning related policies, issues related to the definitions and its implication, and concerns to the high ambient countries and partially to your country as well. Then I'm going to speak finally about key introduction to the Praha project of UNIB and UNIDO. Now let's start by the driving forces. I think many of you were with us yesterday and they saw the slides. This is the main driving force behind the start for assessing this the future refrigerants. What happened in the year 2007 by adjusting the Montreal Protocol to go for an accelerated phase-out regime of HCFC instead of waiting till 2040 without any milestones in between in terms of reduction. So we have commitments started last year by freezing the consumption to the levels of 2009, 2010, and we're gonna start phasing out from next January by reducing 10% in each country of the developing countries, aiming at achieving total phase out almost by the year 2030 and leaving only service tail between 230 and 240, which is 2.5%, which is still negotiable. And the parties, we're gonna rediscuss this percentage in the year 2025. So it might be reduced a little bit as well, depending on the assessment that's going to happen before that. Now, this is not the end of the story under the Montreal Protocol. The Montreal Protocol parties are discussing seriously and aggressively by some parties over the last few years a very ambitious proposal to amend the Montreal Protocol for the inclusion of HFCs, meaning that the HFC is not an ozone-depleting substance. Actually, it is a replacement to the HCFC, which is an ozone-depleting substance. But they are taking it from the perspective that the HFC was promoted through the Montreal Protocol mechanism as a replacement. So it's the responsibility of the Montreal Protocol to take care of this substance, given that they have the knowledge and the financial and technical mechanism to address this much easier than any other convention, although the HFC is listed under the framework of the climate change conventions, meaning Kyoto Protocol, which is going to be also an issue for the discussion of the Kyoto Protocol next year when they are trying to conclude an alternate or continuation of the Kyoto Protocol agreement by 2015, end of 2015 in Paris. So the discussion within Montreal Protocol over the last couple of years, whether to discuss an amendment for the phase down and not phase out, you have to take care of this term. We are phasing down because we acknowledge that we don't have alternatives that can cover the whole spectrum of all types of applications, and we need at the end to keep some consumption to cover those applications which we currently does not find any suitable candidate to replace it. Or we can come up with a system to how to, within also the Montreal Protocol, how to manage the HFCs without amending the protocol. So those two discussions are being on the table in front of the parties of the Montreal Protocol. If we start to shift from the Montreal Protocol and go to higher level, in 2012 there was what's called the Earth Summit. This is taking place every 10 years. It's a high level, at the level of the heads of the states, globally convening every 10 years to discuss the future of the Earth, the planet Earth. The last one was in 2012, and they adopted what's called the Sustainable Development Concept. And this time they adopted a document called The Future We Want. And paragraph 222 in this document states that they are aiming to reduce the potential consumption of HFCs, and acknowledging its contribution to the global warming as well. And they are supporting for gradual phase down again. So now this is the message is coming from a higher level to the international community and those who are working at the technical level. So apparently there is a strong political message that this issue of the HFC is going to be materialized in a form of commitment in the very near future. This was followed in the year after, in September 2013, by another high-level segment event, which is the G22 summit that took place in St. Petersburg in Russia in September. They also adopted similar text in their declaration, the leaders of the biggest 20 economics, and they have put some additional elaboration on this commitment by trying to distinguish between the roles of the Kyoto Protocol and the Montreal Protocol. It's not explicitly mentioned here, but here it said, while continue to include HFC within the scope of the UNFCCC and its Kyoto Protocol for accounting and reporting of emissions, meaning that the Montreal Protocol can count for the consumption and production, while the Kyoto Protocol only handle the emissions. So this is some kind of a political message how the international community and the technical people should be discussing and focusing their deliberation in the next couple of years. So these two strong political messages were followed by an aggressive diplomatic campaign by several leader countries across the globe who were behind this proposal to phase down the HFC. But the concluding message out of this that apparently HFC, whether it's going to be concluded this year or the next year or in 5 years, is not going to be the future. It might be the very near future for some of the applications, but it's not going to be the ultimate future. One day it will be phasing out of the industry very gradually or very swiftly. We will see now how this is going on while we are discussing more. There's some complications between how to address both the climate and the HFC under the Montreal Protocol in relation to the climate change negotiation. First, most of the currently alternatives to the ODS are within the Kyoto Protocol mandate. So this is one of the legal complications. The second thing is that there is unclear perspective about concluding the agreement for the climate change. We don't know yet whether an agreement will be concluding. Although of all these political campaigns, and you have maybe heard about the recent UN summit in New York about which was called by the UN for the climate change. And despite of all that, we don't have any clear commitment that the world will be concluding a clear agreement next year. They have committed to do so, but they have committed to do so also 3 years back in Copenhagen, and they failed to do it. And another issue is that we don't know yet the role of HFC in any future climate change arrangement. And even if they concluded next year, the HFC contribution to the greenhouse gas emissions is more or less 2 to 3%. So it's not a priority in the list of the greenhouse gases in front of the policymakers within the climate change negotiation. So even if they concluded next year or the year after a climate change mechanism and an agreement and convention, we don't know whether it will include an HFC or any arrangement for the HFC or not, because it's not a key priority there. Also, we need to understand that there is undecided relation. Till today, we don't have official legal communication between the two conventions. There are some kind of invitation to attend, reciprocal attendance of the events, but there is no legal communication to start discussing this issue seriously. So this is also an issue that takes some time, because Montreal Protocol as it stands, it is called the Montreal Protocol about ozone depleting substances. So there's a legal issue of introducing a substance which is not an ozone depleting substance within the. Sorry about discussing all this politics, but I believe it may be very important to you to understand the backgrounds of what's going on in the industry side when we are going to discuss it later. Now, finally, we don't know yet about the implication of adopting a phase-down regime. We used to adopt a phase-out regime, which is very clear and easy. We can do a ban, we can start to control the market, do a quota, reduce. But conducting a phase down, this will give us more complication in handling some of the sectors, like the servicing sector, like the small consuming sectors and SME sectors and all this stuff. It will be very difficult to control. When you set a target to ban, you know that you're going to close the tab one day. But if you set a target just to partially close the tap, you need to be careful that it is partially closed to that, the level you are looking for only. Now, another driving part of the driving forces is looking at what's the current trend in the industry. This is extracted out of the Technical Option Committee, Refrigeration, Air Conditioning Technical Option Committee quadrennium reports that, and this is from the 2010 report, because the 2014 report will be released, I think. Bassam, we are privileged to have an RTOC member with us, Mr. Bassam, and he just told me that maybe the next report will be released early 2015. So, but currently, the current situation, more or less, states that in the majority of Article 5 countries, which are the developing countries, R22 is still the dominant refrigerant for most of the air conditioning applications, except, of course, the chiller sectors. Chiller sector, I think, converted to R34A since a long time ago, with few amounts that goes to liquid refrigerants like 123 or some newly developed ones. But R22 is still the dominant. There are some attempts in some developing countries and developed countries to introduce seriously hydrocarbon and 32. I'm going to talk about both of them very shortly, but not yet widely and commercially available. But we assume and believe that they will be commercially available, at least in China and Japan, in a wider scale in a very near future, talking about 2 to 3 years time scale. The carbon dioxide, HFC 161, and other long list of refrigerants are being examined, but only at experimental and laboratory levels, and nothing yet predicted to be introduced to the commercial sector in terms of refrigerant. I'm talking only now about the air conditioning industry. I'm not talking about the refrigeration, and only residential commercial air conditioning industry. 410A, apparently still the dominant in most of the developed country. 47C is losing its ground, and it's almost phasing out from most of the air conditioning industry, except some few in developed countries. The Article 5 or the developing countries have already the capacities to introduce 410A, but they were not introducing it because R22 was still allowed in the majority of them. So we're manufacturing 410A only upon request by local markets or for export to non-developing countries markets. So other candidates now being discussed, majority are with what's called the HFOs, hydrofluoroolefins, which is a new group being invented by the refrigerant manufacturers. We're going to speak about it in a few slides, but not yet, nothing yet put into the commercial production lines, and all still under the testing and examining. And part of that, those refrigerants you will see are examined within the high ambient project. Now, in a nutshell, we can summarize that most of the developing countries are still using R22. 410A manufacturing ability is available in developing countries, but not mainly for the local markets. And China is preparing itself for the hydrocarbon production. This is the direction in the developing countries. In Europe and North America, the 410A is the dominant as a refrigerant for air conditioning applications. But there are different trends in terms of what's to introduce next after the 410A. There are the examining of the HFOs group and the examining of the hydrocarbon, particularly by Northern European countries. In Japan in particular, they took different paths, and they are decided after long discussion and assessment process, the introduction of what's called HFC 32. It's part of the HFC group, but it has a lower GWB compared to the 134A and 410A. So they understand that this is a very good transitional solution that can take them at least 20 to 25 years or maybe more safely before considering again rechanging to a different refrigerant. So unfortunately, this figure shows that the industry of the air conditioning is facing a real dilemma. 10, 15 years back, we didn't have this problem. It was only R22 and that's it. So now we are having different candidates, and looks like that the markets will be faced by different types of application could be available in the same market with different refrigerants. And we understand the limitation of the servicing sectors and the capacities available there to handle multiple refrigerants for the same application in the same market. And that's why this was one of the driving forces behind the project and initiative we are discussing in this presentation. In terms of how this was transferred into formal policies, most of the developing countries does not have yet a policy to start banning HFC 22 equipment, except I think many of you heard about the initiative of Saudi Arabia they took recently that starting the ban of HFC-based equipment starting from 2015, which is a couple of months from now. It's a very challenging task, and we wish them all the luck. Away from the developing countries, in US, R22 is banned from sale manufacturing for the US market starting from 2010. However, it is allowed to be manufactured for outside markets in condition it is shipped flat, meaning that without refrigerant. And this is causing problem to many countries because it is increasing the consumption at the end of the R22, instead of having the machine already shipped with refrigerant. The rest of HCFC, and mainly we are talking here about 1 to 3, which is the other one used for but only by limited types of application for air conditioning centrifugal chillers, will be banned totally by the year 2020. For the EU, maybe we heard yesterday a little bit a hint from Didier about the new F-gas regulation recently adopted. But apparently the F-gas regulation will take the industry of the air conditioning to a different dimension. Because according to the it's not easily related to the ODP or the refrigerant, it's related to the CO2 emissions. However, by interpreting this emission into clear policy that is understandable to people, you can easily say that movable air conditioning units with refrigerants less than 150 GWB will be banned from markets by the year 2020, and unitary units, which is the majority of equipment, with candidates of refrigerant less than 750 only will be allowed, starting from the year 2025. This second point is very important for us because 750 means 134A is out of the equation, 410A is out of the equation, 407C is out of the equation, 404 is out of the equation. None of those will be in the equation. We only left with newly developed refrigerants plus the HFC 32 and the hydrocarbon. This is the only candidates now available that Europe will have to deploy for air conditioning unitary systems starting from the 2025, meaning that they will work earlier, of course, but 100% by 2025, no more HFC-based equipment in Europe. Okay, this is the map of the refrigerants, which was available over history. The first group on the left side of the screen is part of history, including the R22. It's available now, but it's going to be a part of history because there's a commitment and compliance. They will be going to be phased out. So we cannot rely on them as a candidate. So we are left with the higher GWB HFCs options, 134A, 410A, 407, but there is a big question mark about their sustainability and at the long term. So this is the remaining options that we have now. So let's look closely, have a closer look on those options. It comprises of 3 different categories. A single component category, which include the 32, 1234YF, which is not suitable for the air conditioning units. It's suitable for the mobile air conditioning units, cars air conditioning units. And this is adopted by different car manufacturers in Europe now. And something called 1234ZE, and recently 1234ZD as well, which is a liquid refrigerant to replace the R11 and 123 for centrifugal large chillers only. And the second group is a combination of HFC and HFOs, blend. HFOs is called hydrofluoroolefins. It's a new group invented by refrigerant manufacturers that has less atmospheric life. So it has very low GWB impact, most likely between 500 and below in most cases. They don't have yet an R numbers. They are being introduced under commercial numbers by 2 to 3 companies across the globe. DR's numbers, L's numbers, and other options. All of them are still under examination. None of them were put yet to real production in any of the industry worldwide. And finally, we have the natural options, which they are called natural refrigerants. Propane, which is the R290, carbon dioxide, and ammonia. And there's a lot of limitation, except apparently the propane seems that it's gaining ground as a long-term alternative, particularly for smaller units. Till today, we are talking about less than 24,000 PTU, which will be mostly the candidate suitable for deploying hydrocarbon refrigerant as refrigerant for this type of application. And already industry in China and India started to have completed the trials and completed switching some of their production lines, and they are ready to start introducing it to the market maybe within a few months from now. So this is the short list, as we mentioned from a while. And the last point I would like to talk about it in the driving forces is the definitions. Now we'll go to the issue of the high ambient. When we first talked about this high ambient issue, it was 6 years back during the amendment. And at that time, there was no definition. We used the term aggressively, globally, but we didn't define it. What do we mean by high ambient? It continued to be debatable till last year when we formulated the project formally, and we concluded that the high ambient, it's only countries who are designing air conditioning unit for T3 conditions, which is the 46-degree outside temperature design condition requirements. And many countries are having hot climates and high ambient condition or humid condition like South Asia and others, but they don't design for this operating condition. So this is the reference now for what we are calling high ambient. And this is the ISO standard, and this is the ANSI HLI standards, which is also adopted by SASO. They are all adopting the same T3 condition design characteristics, which is 46 outside temperature. The other undefined term globally, which is now being debatable as well, is what's meant by low GWB. What is the value of this law? There were two attempts to do such a classification for the values of GWB. First attempt in the year 2010, but it was very long list categories, and it was very difficult to digest. Also, the second attempt in the year 2012 by the Technology and Economic Assessment Panel into two groups, low GWB alternatives and medium and high GWB alternatives, but still acknowledged but not yet followed and accepted by the industry and the policymakers around the globe. So till today, this term is undefined, and you can hear some people talking about lower GWB. It's a proportional term instead of using low GWB. And we heard sometime in New York earlier this year, researcher and industry talking about lower GWB options, and it ended up to have discussing option with more than 1,000 GWB alternative. So the concerns of the high ambient countries in nutshell, and I think it's the same for the Lebanon as well, is the sustainability of any new offer. If I'm going to adopt something today, I think it's enough for the industry to keep changing every 10 years to different refrigerants. It's creating a very big chaos to the industry. Availability of the components. I can easily say the hydrocarbon is a great option, or ammonia is a great option, but do we have enough components to serve this option in terms of compressors and all the required manufacturing components needed for the units? The cost implication of the final product, the market readiness to handle and service this type of refrigerant, harmonization of policies among the different countries because we have common markets and interlinked to each other, and applying single solution for each category, as we mentioned earlier. We cannot accept that we have split unit in Lebanon. Some of them are with R22, some of them with R410A, some of them with hydrocarbon, and some of them with R32. It's going to be a problem, a real problem, and it will increase the consumption dramatically in the country and create a lot of problems. Similarly, the policymakers have more or less similar concerns, but from the policy perspective, including how to link all this work as well with the energy efficiency programs, which are being introduced lately as a very urgent priority to many countries because of the energy scarcity that most countries are facing, as well as the physical implication on economics and public budgets. Another concern for the high ambient country, as I mentioned, is the energy efficiency. This graph is taken from a regional study that shows that the Gulf countries in 20 years, between now and 2030, will need power plants that worth 120 billion to cover the demand in the cooling sector only in less than 20 years. So without doing some serious work on controlling the standards and the energy efficiency requirements, this demand cannot be met. Now, I think I'm going to stop here. I have only 2 slides for the high ambient project, but I will leave to Dr. Walid to speak more about the high ambient project, because I think we are running out of time. But in general, it's a project to try to assess the future technology through a collective approach. Collective approach meaning that we have the whole industry, most of the industries in the high ambient countries with us in the region. This is quickly, how many companies do we have manufacturing participating in the project in the region of the West Asia, and how many international technology providers are providing their support and materials and technical assistance to help in putting this project forward. And we believe that we hopefully going to have the final results sometime by the mid of 3rd quarter of next year, inshallah. Some of the other issues related to the project may be further explained by Dr. Walid. And thank you for your kind attention. We're going to conclude with a couple of slides at the end. We apologize for that I take maybe longer than expected. Thank you so much.
Thank you. Thank you, Mr. Ayman, for that. Welcome again, Dr. Walid Shakroun, coming from Kuwait University. He's a fellow of ASHRAE and has a lot of information to provide us today. Thank you.
Thank you, Samir. Thank you, Ayman, for this nice overcap of all the refrigerants, highlighting many challenges ahead of us. 22 will not be there. The call really to phase down HFCs, meaning there is a lot of refrigerants, 410, for example, one of them that's currently been probably used, will not be there, or there is a call to phase it down. So solutions, this is what we're looking for. Companies now are in the era of really hesitant of what to do, where to move next. I think this project kind of addresses these issues. We're on the track of doing some research to come up with future refrigerants. So I speak a little bit about insight into high ambient. What do you mean by high ambient? As Ayman mentioned, people understand high ambient differently. I speak about Praha projects, and I'm not sure if I will have time to speak about the Arab project, which is another research underway, taking place right now by HRI, to kind of looking into looking into refrigerants and assessment and so on. More into this slide was shown by Ayman. You could see that what we mean by high ambient. We're speaking about countries that the temperature could reach 50, 55 degrees C, and we'll see later on that what we define by high ambient really is the design conditions, not by the maximum temperature. This is really misleading terms. People think that why you're doing 46, for example, even though in Kuwait may reach 55 the temperature, or in Dubai it may reach 51 or whatever. So I think just to show that ASHRAE has classified zones, and 90.1, 90.2, when they speak about efficiency of the machines, they speak about zone 1, zone 2, zone 3. And if we look at zone 1, for example, which is defined by ASHRAE as being very hot zone, they really calculated the cooling degree days. And by the cooling degree days, they could really classify this country, whether it's in zone 1 or zone 2 and so on. But in ASHRAE, they have said anything above 9,000 cooling degree days is classified as being zone 1. Now the question is this really fair to our part of the world? Because in our part of the world, we'll see later on that instead of 9,000, we may reach 13,000. Now all of us are in zone 1. Is it really fair to put, for example, efficiency at 9,000 cooling degree days? What about if the temperature, if the CDD go up to 13,000, for example? So here we're calling into, we have zone 1, but we have, probably zone 1A, zone 1B, and zone 1C, and so on. So really above what ASHRAE has classified. And this is really a message we are bringing inside ASHRAE to say we have to classify differently when we go above zone 1. For example, if we look, for example, at Kuwait, we could see a maximum temperature of 49 degrees C. So 49 degrees C is not really, by ASHRAE definition, is way above zone 1 that they have mentioned. The cooling degree days, for example, is 11,500, something in that range. So ASHA puts values at 9,000, but here in Kuwait, for example, is a lot more than this 9,000. The cooling temperature, again, the design cooling temperature is 46 according to ASHRAE's criteria. Dry bulb 1%, for those who are doing some cooling laws, they know what I'm talking about. So the design conditions is 46. And again, in every country there is misleading about why 46, why not going more. So the country, if they're not really into the business of air conditioning, the business of design, though those policy makers, they say, no, let's put the design conditions higher than this because the temperature go above 50. By putting, the design conditions, when you bring it 1 degree up, meaning the cooling load will go so much high, meaning you need more energy. So this is really a very important term that we should be aware when we address it to the policy maker. Now, how the AC will perform when we speak about high temperature? I mean, what happened? So what if we make it 46 or 48? For those who are, in the air conditioning business, they know that it has big effect on the EAR and on the kilowatt per ton efficiency of the machines. Let me here be clear about definitions. Go back to my class. What we mean by EAR values. EAR is capacity divided by power, but the units are different. So we speak about BTU, which for the capacity per hour, and watt for the power of the compressor. But when we go to some countries, they use kilowatt per ton, which is another SI units, meaning the same. There's only conversion factor between the two. It's the other way around. It is kilowatt per ton. So the cooling is in ton. The power of the compressor is measured by kilowatt. So when you hear EAR, when you hear kilowatt per ton, they're almost, the different trends. But you can go from one to another by simple conversion. And of course, COP, as we all know, it has no units, where we speak about cooling per power, both in the same units. So COP has no dimension. The machine behaves differently at high ambient, and this is very important to see really, if I bring a machine to the lab and I increase the temperature outdoor from, for example, 35 to 46, you can see very clearly that the cooling capacity will go down, sharply. So the same machine will give you, for example, 2 ton at 35. It may give you 1.8 or 1.7 ton at 46. So the cooling capacity goes down with the temperature, no matter what the design of the machine is. Anytime the temperature go high, the cooling capacity will go down. Now, not only the cooling capacity, but also the power of the compressor. So here we go. We're losing capacity, and also we need more power for the machines. So we're talking about two different, more energy and less cooling capacity. So putting that in the EAR value, you can see the EAR goes down. So what the machine, when we speak about EAR value, for example, at 35, it's going to be different at 46, and we see a big decrease at the EAR. This is very important. This is really what the essence of the whole presentations and talks that Ayman has mentioned, that when we go to a higher ambient temperature, the EAR value is really, we're speaking about different EAR value range. The kilowatt per ton goes up by the same conversion factor because it is really the watt divided by the ton. Now, this is from our lab. We measured units ducted split at 46 degrees C, and you could see the shift between 35 and 46. We are losing about 25–30% efficiency. So we lost already efficiency by this amount for the ducted split when you go from 35 to 46. And you can see that the data points depends on the design of the machines. These are for many machines. They're close to each other, so you could really put a trend in there. Meaning, if I have to make a conclusion out of this, the design by the manufacturer does not really make much difference between, for example, machine A, machine B, machine C by different companies. They're all losing the same range of the efficiency. But mini split also, it has an efficiency of 30%, for example. There's variations here between machine to another machine. If I go to package, also there is some loss of the efficiency, about 30%, meaning ER values can go down as high as 30% from 35 to 46. I want to go back to mini split and probably mention something here that the design may have something to do with it. So when we compare refrigerant to refrigerant, we have to make sure that the company that's designing this machine is the same, because it's not really fair to say, for example, the refrigerant gave us higher or lower compared to the same. So systematic way of doing research is very important in this topic. We've seen companies saying, comparing company A to company B, it's not really fair comparison. You have to compare the same company with the same design when you go from one refrigerant to another refrigerant. When we speak about standards here, as Ayman has mentioned, we are phasing out 22, so 22 will not be there. This is one challenge for us, ahead of us. We have seen also that countries in the Gulf region specifically, policymakers, do not know much about the business, and they keep on saying, no, we want to have more efficient machines. At the end for them is economy, and for those who are in the business of looking ahead of the vision of the Gulf countries, for example, Saudi Arabia will not be able to transport oil by 2020, okay? Probably only 20% of their oil could be transported because all the oil will be consumed inside Saudi Arabia. And for the country like Saudi Arabia, and this study was done by a British company, so they say, alerting, Saudi Arabia will not have oil to export in 2020, much export. Kuwait, for example, the study could go from 2040 to 2050. So those countries suddenly, they say, we are really in a bad shape. Down the future, we're not going to be able to sustain our future. We need to do something. They look at the sector where the energy is spent most. It is in the air conditioning system. Let's increase the machine efficiency. So they said we need to increase the efficiency of the machine. Another, of course, challenge that we have ahead of us is the call by the United Nations and by other multilateral agencies to phase down HFCs and to go for low GWP. And we all know that low GWP, you know, the machine will not perform as good as 22. 22 was an excellent refrigerant as far as efficiency is concerned. So these are very important three challenges that are ahead of us. Efficiency of the machine, the country is pushing it up. 22 is not in the market anymore, and calling to go for low GWP refrigerants. This just a slide I want to just show you the last one here, the AR values. You could see ASHRAE 90.2 put 13 for the ER values. Now 13 at 35 degrees C. However, for example, Kuwait, they put 7, but 7 at 48 degrees C. Dubai put 9.5, United Arab Emirates, 9.5 at 46. Kahrama in Qatar, they put 8.5. Saudi Arabia put 9.2. So those are very challenging numbers at high temperature. So for a country like Saudi Arabia, for example, to say I want my machine to have an efficiency 9.2 at 46, this is a big challenge for the industry. So this is really something that we need to be careful about. Now ASHRAE say 35, because for ASHRAE, again, zone 1, if you go back to my previous slide, zone 1 was, but for ASHRAE is okay, you could maintain 13 at 35. So I really did not look much into high ambient, what we call it high ambient. So you can see variations in the company, in the countries on the ER values. Kuwait, for example, they say we want 7 for our ER values. This is 7 in here, but at 48 degrees C. This is also a very challenging, companies in Kuwait, they are really saying we cannot do that with the phase out of the 22. Without 22, what do we put in the machine to give us this kind of efficiency? We cannot sell any machines in Kuwait if we keep on doing this without the 22. So, and also they need to be tested at 52 for, to make sure that the compressor does not trip. This is an endurance test. This is no problem, we could meet that one in there. But the issue really is the 48 and the efficiency of the machines. Now again, I want to make sure that you guys understand what 46, why 46 in there. Because we believe, even though the temperature can go high in the day to 50, 52, but the design 46, because the time lag, the walls are there is a time lag between the temperature outside and the high cooling load inside the house due to the mass structure of the house. For example, this is, we want to maintain a temperature of 24 inside, we want to keep it cool, the room. The outside temperature go high. This is one typical day, for example, from 35 all the way down to, all the way up to 46 or 48 degrees C, and then it goes down during one day in July, for example, in high temperature. This is the temperature outside. But if I put down on the AC capacity, as we said earlier, the cooling capacity goes down with the temperature. So the cooling capacity used to give us this much at this temperature, 35, but now it's going to give us a lot less, and this is a curve of the same machine during the day cooling capacity of the machine. So looking at this, you could see, meaning in this day in here, in this time, I cannot get this one here. Here you go. And this time in here, I will not have cooling. I will not have cooling. That means we need to raise the cooling of the machines. However, when you put the cooling load of the house, when you do some cooling load in the house, you could see that the cooling load versus time do change. And there is this time lag that I'm talking about here between the maximum temperature outside and the cooling load of the house. So there is a couple of hours time lag. Putting, again, the cooling load on the on the curve again, you could see now really the problem that you may have cooling, if you keep it 46 for Kuwait, for example, is only very small, and it's only half an hour a day. So to call design conditions to 48, that means you're going to shift all this load up, more energy will be needed, and the Kuwait, 70% of the energy goes to cooling, so meaning Kuwait will need probably 75% for the cooling load and so on. So going into Praha projects, Bassam is telling me that my time is up. Huh? He should be telling me this, not you. For Praha, this is one solution to go for the low GWP. As Ayman mentioned, the project that we have ahead of us, the challenge that we have ahead of us, we have many companies involved with us. Ayman mentioned the companies, compressor, technology providers, manufacturer, and we're looking into assessing machines and the ER of the machines for different refrigerants. And those are the categories of the air conditioning system that we will be testing: window, decorative split, and ducted split, and package. We have 4 different categories. And the refrigerant that we'll be testing, 32, Ayman mentioned why 32 is not really a low GWP, but it is lower. So 680 will be accepted at least for the next 20 years. So let's see the performance of 32 for high ambient temperature. We're going to be testing 2 HFOs, and then we're going to be testing also hydrocarbon 290 is a future refrigerants. Of course, every one of those have its own challenges: flammability, low flammability, and then the idea of hydrocarbons, high flammability. So this is something that we have to deal with, but we're looking only from efficiency point of view. Of course, every one of those will be tested based on the baseline. So company A, for example, do 22, and then we'll do one of those refrigerants. So this way we could compare the refrigerants to the baseline case. At the end, we're going to be testing 82 prototypes. They all will be shipped and to the same lab, tested at the same company. So this would really give it some integrity to our projects, and to make sure that the results that we're getting are meaningful and worth coming with a conclusion. So we'll test in an independent lab. We're all going to be testing the same thing for the thermal performance. And we're going to be testing those machines at 3 different temperatures, 35, 46, and 50, to really see the curve and to make sure that we understand the behavior of the machine in this range of temperature. And the indoor temperature, Ayman has mentioned, we're going to go with the standards of AHRI and with ISO on the, how to test them and so on. Endurance tests will be done according to standard. The lab that will be testing those are a very verified lab, and we made sure of that. We cannot tell you the name of the lab, but at least this is, it's an internationally well-known lab. And we're going to get so many data from this lab, not only the refrigeration cycle behavior, but also on the performance cycle. So we're going to come up with the ER values, with the pressure of the refrigerant, high pressure, low pressure, temperature at all the cycles, and so on, to really understand the behavior of the refrigerant inside the machines. Other project, I will not have time to go into it, so I'm not going to do it. Basically, there is a project called AREP underway, but it's a really different one. The testing is done in the company for different range of air conditioning systems. But if you read about it on the net by HRI, this is another project that's underway. So I'll leave Bassam to complete. Thank you.
With the short time left, Mr. Bassam will go ahead for the last part.
Thank you. I'll try to be brief. Basically, when the project was being presented, we were asked the question. UNIP and UNIDO were asked the question: why are we looking only at residential units? And what about other, other technology that's available in the region? The question came because Praha included other research as well, and part of the research is the assessment on the feasible technologies that are available in the area. And so the idea of district cooling came around, and said there are many district cooling projects in specifically in high ambient areas. So what is the effect of having district cooling in the region on the phase down of R22, basically? So this is what prompted the study. And also we wanted to understand the impact on the emissions, on the CO2 emissions of using district cooling, because as district cooling, basically the idea for district cooling came. Today the installed systems are around 6 million tons of refrigeration, or 14% of the 43 installed systems, 43 million tons. Sorry, we're talking in tons. If people want to understand kilowatts, you have to multiply by 3.5, almost by 4. And 45 of this installed capacity is in the residential sector. The reason we're putting all these figures is to understand that district cooling is not just for large projects which are fully commercial or industrial. That's how they started. 45% of them are in the commercial sector. Actually, also the planned projects until 2030 cover a construction market of 1.5 trillion US dollars. Ayman showed 50 billion, a figure of 50 billion. This is in the construction industry. So we did a quick calculation and we estimated that this 1.5 trillion, since most of it will be air conditioned, will be about 38 million tons. Now, just to give an impression for the non-HVAC people or an idea, a room like this is what you think, 1 ton, 1.5 ton? Yeah?
People here?
Would people here? Okay, let's say 2 tons, so it'll be like 19 million rooms like this one that we're talking about until 2030 that are going to be built. That's the way I understand it. Okay. In here, I would like to acknowledge, I don't see Maroon Khouri here, but he helped in, I was inspired by him because he's a beacon for district cooling, but if some people from Dar are here, please convey my thanks to him. 60% of the power requirement will increase 60% for these 38 million tons, the equivalent of 1.5 million barrels, and this is what Walid was talking about. Now, the good thing is that the district cooling will reduce the peak power demand by 50 to 87%. This is a study that was done by DAR. We're almost out of time. And when coupled with the reduction, and that's very important in direct emissions, so we're talking reduction of direct emissions and indirect emissions due to the power consumption, each ton of refrigeration will contribute to a reduction of an annual reduction of 3 metric tons of CO2. So that was one of the big conclusions, that by using district cooling, we will be able not only to reduce the power consumption, but also to reduce the direct and indirect emissions. There are challenges to district cooling. I don't think we'll have time to discuss them, but basically it's the coordination between the developers and the government and having the right approach on how the billing is going to be done. And this is what I wanted to show you. For those of you who have attended yesterday's session, the industrial session, and listened to Mr. Mazen talk about ODP, the ODP ton is the weighted equivalent ton of the effect of of R22, so that we understand it as an ozone depletion weight. The phase 1 of Lebanon is 20 ODP tons. Now, the effect of replacing existing H22 systems by DC plants will be equivalent to 137 ODP tons, or in metric tons, you have to multiply by 22. And additionally, 38 million tons, the 38 million tons that are going to be added until 2030 will also contribute to a reduction in emissions by 114 million tons of CO2 equivalent. So if all these 38 million tons had to go as 22 on individual rather than district cooling, we would have contributed 114 million tons more. And the other equation here is that also the effect, what we're saying is because of the the district cooling, they have an excess capacity. So the installed capacity already of the 6 million tons that we have seen will also contribute to a reduction. If this installed capacity is used to replace existing plants, will contribute like 30% or 37 ODP more to the reduction in CO, in 22. Well, there are other benefits as well: economic, societal, and environmental. Just one more thing before I leave, please. This is not a competition, but I know there are 3 sessions, but there's also a session in the afternoon, industrial session in B1 in College Hall, and you're all welcome to go there. I know it's a little bit far, so that's why I remind about it. Thank you.
Thank you, Osama. One more comment?
No, it's just the concluding slide for the 3 presentation. Actually, we have the result of this and the conclusion of this. We have 2 messages that we need to deliver. One is message that we are trying to deliver to the technology provider globally, that whatever they are doing, the future refrigerant we want, of course, need to achieve the performance needed, achieve the requirements of the development, achieve the environmental needs, and be safe to use, economically affordable and cost efficient. But the most important thing is to be sustainable. We don't want to be faced by a rapid change every 10 years of the refrigerant. It's enough, I think, over the last 30 years of changes in refrigerants. The second message that we are trying to outreach to the local industries, there are actually 4 messages. First one is that you should be part of the research business. You don't only sit in the seat of the recipient of the technology. I know that we have limited capacities in terms of the compressor manufacturers, refrigerant manufacturers, but the rest of that, we have the capacity to do the adequate research to investigate the future. We don't wait till the future come to us and by force from the commercial side and the technology provider. The second message is that whatever we are going to handle in the refrigerant should not be away and separated from the work in the energy efficiency. They are very interlinked, and they need to be considered together now in one pot. The third message, that without considering a proper institutional technical setup in terms of the standards and norms and codes, whatever we are going to introduce in the future will be questionable and doubtful, because the future refrigerants apparently coming with hazardous characteristics. So we need to prepare all the technical requirements in terms of the standards and codes needed for handling these types of future that we are going to face. And last, that we need to think outside the box. We should not only focusing only the conventional vapor compression cycles. We need to think outside the box. We need to find non-if gases solutions. We need to promote further those types of solutions, because this technology is within our hand, within our outreach and research capacities, and it will be easy for us to rely on it for at a longer term. Thank you so much for your attention. We left some questions for you for the opening the discussion. If we have a few comments or questions, we are be willing to take it from your side. Thank you so much.
Thank you again. For the sake of time, unfortunately, there would be only one question, because, and the 3 gentlemen will be staying here all day, so if you have a direct question, you may
not
go.
all day. Samir?
Yeah. Yes, please. No.
Okay, good.
Okay. Go ahead, please. Okay.
I want to thank you all for your perfect presentation. I have a concern about district cooling. If you want to make it a public thing, then what about the cost of all the infrastructure you want to do to put it in place? I think this will overshadow the benefits. It's good for localized cities or, you know. But
You misintroduced your name first.
It's widespread. I think it's...
You misintroduce your name first, please, and the capacity.
Zaki Zatari, board member, actually board member and engineer.
Thank you.
Yes, well, thank you for the question, and I'm sorry we didn't have time to discuss the challenges. Definitely, this is one of the challenges. I just can relate to one example, which is in Dubai on Sheikh Zayed Road. I think everybody knows Sheikh Zayed Road is the main highway. There, most of the buildings had already their own air conditioning, and then Tabrid at that time, they put a plant in there. And they were connecting to the new buildings. It was a challenge because, you know, by the time at first they connected to the new buildings, and later on they started, whoever wanted to, you know, convert their existing, they were connecting to it, and of course they had to come with the correct argument. But definitely the challenge of having the infrastructure there to make sure that, you know, you're working with the government so that you become like a utility, like the water supply, like the electrical supply.
Big cost to put all these big pipes.
Absolutely.
But the installation now, the power grid is already there.
Yes.
Well,
It's-
thank you very much. You have an input? Yes, please.
I have two very good questions, one to Ayman and one to Dr. Walid. First to Ayman, I know that you are working with GCC countries, and the move now is to air conditioning system, which is the most popular and big industry in the Gulf region. What are the strategy for phasing out on R22 the air conditioning system in the coming 5 to 10 years, because it's going to phase out? So are we going for HFCs, with the HFCs issues or phase down, or are we going for my other question is to Walid is, you're talking about the highest temperature in your of 48 degrees, but I know in Kuwait it reaches 55, in Iraq there is 57 degrees. So why it's always 48? Because most of the industry, compressor industry, we are working on the highest temperature of 48. While in Kuwait it's 52, 55 something. In Iraq and in Basra it is 57 degrees. So your estimates are based on this peak temperature will not help them.
Just a short answer. Currently, there is no unified or single policy for of the equipment of R22 and which technology to replace in most of countries except for Saudi Arabia, as I mentioned. They took an aggressive decision to stop importing and producing R22 based equipment starting from January 2015.
Don't you think they will be facing big problems?
Yes, they will be facing, we expect so, but it's of course a country prerogative to take their own decision. We cannot interfere. And that's why this project was initiated, to help the countries within 2 to 3 years to see their future on the road, in order to take a sound decision based on technical assessment. I think the other question, Walid can easily reply to it. Yeah, please.
Yeah, I think this is a message we're trying to say, that when the temperature goes high, the house takes this heat and store it, and bring it inside the house, inside. There's a 2 hours time lag. So maximum temperature 52, 53, 53 does not mean we have to rate our design conditions, because designing, remember, the curve is so high and it's so peak. We cannot shift the peak higher, meaning we have to shift the whole curve high. You need lots of energy to put in. So that's what I try to show here, that even though you may suffer for half an hour, where the inside could reach 45.5, 24.5, instead of shifting everything up and then pay, remember 70% of the energy.
Well, thank you very much once more. I'm sorry for stopping at this stage. There will be an immediate session after this. Maybe 5 minutes break. Following session. Thank you very much for attending.
Thank you. شكرا سمير.
I'd like to welcome the newcomers as well that are here since morning for this particular technical session number 5. We'll be having, theoretically speaking, 4 presentations. due to the time limits, I'd like to ask each presenter to allow, let me say about 20 minutes. If there will be a couple of questions immediately after that, that would be entertaining the entire time. So our first presentation is about ground source heat pump systems for residential buildings in warm climates, energy, environmental, and economic consideration. I'd like to welcome Dr. Micropoulos Apostolos. I apologize for the misspelling. The presentation is, as I said, the ground source heat pump, and Dr. Apostolos is a senior researcher in the Department of Environmental Science and Technology at Cyprus University of Technology, Limassol, Cyprus. Yes, please.
Thank you very much, Dr. Tarbushli.
In return.
I try. Good morning, ladies and gentlemen. To begin with, I would like to mention that this study is primarily based on the climate condition of Cyprus, which can be characteristics for the Mediterranean climate region. Based on that, the results of this study can be easily adapted and applied to another areas with similar climate conditions, such as Lebanon, Malta, southern Greece, and so on. In Cyprus, the residential building sector accounts for almost 16.7% of the total final energy consumption. And these energy ranges are mainly covered by electricity, oil, and LPG, while the remaining 15% is served by renewable energy sources, mainly for the production of hot water. Since 1995, the residential sector of Cyprus has increased the total energy consumption by 3%, while the CO2 emissions remain constant. With this framework, Cyprus, as a member of the European country, is obliged to adopt measures in order to improve the energy efficiency, reduce the CO2 emissions, and increase the share of renewable energy sources until 2020. Ground source heat pump systems are recognized as one of the most efficient technology for space heating and cooling. In recent years, the worldwide capacity has been grown rapidly due to their advantage, and it is estimated at 35 megawatt installed thermal capacity in 2010. This is the recently published available data. In contrast, Cyprus, the installation of ground source heat pumps remain limited. It is estimated that we have now about 160 installations, which account for 9.5 megawatt thermal installed capacity. And these installations are mainly in residential buildings. It is expected that a wider application of ground source heat pumps in Cyprus energy system will be beneficial, not only improve the energy performance of the building, but also increase the energy independence of the country, which is a big problem because Cyprus is a small and isolated energy producer country. The aim of the study is to evaluate the energy, environmental, and economic benefits derived from the application of ground source heat pump systems in a single-family residential buildings in Cyprus in terms of primary energy consumption, CO2 emissions, and economic benefits. For this purpose, a single-family building of the country was defined, and its energy performance was modeled when a ground source heat pump system combined with a vertical ground source heat exchanger, a two common convectional system, an oil-fired boiler or an LPG-fired boiler, and an air-to-air heat pump was applied. The first step of the current study is the design of the typical single-family building. With regard to the local architectural features, it is developed in two levels, which are connected with internal staircase. In the ground floor, a spacious living room, a study, and a kitchen are located, while in the upper floor accommodates 3 bedrooms and a sitting area. In total, the building covers about 100 square meters. The building is freestanding on the pole, therefore the windows are located in every facade, and the majority of them is positioned in the main facade, which is oriented due south. More specifically, the load-bearing structure was made of reinforced concrete and masonry built with hollow clay bricks. The external opaque vertical elements were insulated with expanding polystyrene, which are positioned on the external surface. The building roof are flat, thermally protected with expanded polystyrene, which lies above the protection layer, and it's covered with gravels. The ground floor is in contact with the ground, and it's thermally insulated with expanded polystyrene below the concrete slab. The thickness of the thermal insulation for each building element were calculated in compliance with recent building energy performance regulation of Cyprus. The energy requirements of the single-family building have been calculated with the aid of Energy Plus software. For using the typical meteorological years, which is provided by the Meteornorm database. In order to estimate the benefits of ground source heat pump installations in Cyprus, 5 characteristics location of the island is selected. This area is Nicosia, which represent the mainland of the island. Larnaca, Limassol, and Paphos is placed on the southern coast of the inland, and Saitas represent the mountainous climate of the island. Then the building was derived into 11 independent thermal zones, and for each zone, the capable indoor conditions was applied according to ASRA recommendations. Obviously, as we can see from the figure, the cooling load is much higher than the heating one, because the study is focused on the warm climate conditions of the Europe. We can see that the only area with the same, we can say, demand is Aitas, which is, as we can say, in the mountainous area. The dimensioning of a ground source heat pump system is based on the design, heating, and cooling load of the building, which has been calculated with the aid of Elite HVAC software. The required ground source heat exchanger length was calculated using the monthly load profile, which has been retrieved from the Energy Plus analysis, and using the EED design software. Moreover, it was assumed that the ground heat exchanger was consist of double U-tube pipelines, and was filled with the thermal enhanced crude in order to improve the thermal conductivity between the borehole and the surrounding soil. The electricity and the results of this calculation is faced in this table. The electricity consumption of the geothermal heat pumps was calculated using an in-house developed and validated code. Moreover, the amount of electricity that consumes from the circulation pump was calculated with the aid of the methodology for the decentralized circulation pump system proposed by SPHERE. Based on these results, the higher electricity demand is faced from the Nicosia. Nicosia is the mainland city of the island, and following by the mountainous area of Saitas. Obviously, the lower electricity consumption goes account for the northern part, the southern part of the island, which is Paphos. In order to evaluate the ground source heat pump system and the two alternatives, the oil-fired boiler and or LPG-fired boiler and air-to-air heat pump, this is the common system from Cyprus. We assumed that the boiler efficiency was 0.92 and we'll calculate the diesel consumption of oil-fired boiler or LPG boiler with the aid to the energy needs of the building that we have calculated from the Energy Pulse software. The electricity consumption for the conventional heat pump systems was calculated on hourly basis using the energy requirement of the building and taking into account the energy performance ratio of heat pump, which have retrieved from the technical data sheets of its manufacturer. We use for this analysis the ambient temperature from the typical meteorological years that we have retrieved from the Meteornorm database. Finally, the energy consumption for each fuel was turned into primary energy consumption using the national reduction factor for the Cyprus energy systems. In this figure, the annual energy consumption per heating and cooling area for both systems, the ground source heat pumps with the red line and the conventional one with the green line, are presented. It is indicated that the conventional system consumes more energy than the ground source heat pumps in locations of Nicosia, Larnaca, Paphos, and Saitas. The only location that we have the equal consumption between the three alternative systems is Limassol. More especially in Saitas area, the mountainous areas of Saitas, the conventional system consumes 23.4% more energy than the renewable energy the ground source heat pump does. The environmental evaluation of the ground source heat pump system and the conventional one were performed by the calculation and comparison of the amount of carbon dioxide emitted by each system. The calculation of carbon dioxide emissions was based on the fuel's natural emissions factor per unit of primary energy, which are characteristics from the Cypriot energy system. It is observed that the ground source heat pumps produce higher CO2 emissions than the conventional one. In addition, the emissions of the conventional oil-fired system are slightly less than that of the alternative LPG boiler. It is primarily based on the higher emission. That fact is primarily based on the higher emission factor that the heating oil has instead of the LPG. More especially, the CO2 emissions for the ground source heat pump systems range from almost 19% to 29% higher level than the conventional systems. The higher discrepancy is observed for the coldest area of Saitas, while the lowest one is for the middle climate areas of Larnaca and Limassol. It must be noticed that this trend could not be considered as common for all areas with similar climate conditions, as it is strongly affected by the energy mixture of the power production. The economic benefits retrieved from the installing vertical ground source heat pump system in the private household sector of Cyprus, rather than the conventional one, was performed with the aid of the net present value index. In accordance to the European Union Regulation 244 of 2011, the initial construction cost and the operation cost have been calculated assuming the economic lifetime of the investment equal to 15 years. This is according to the European standard EN 15459. The calculation of the annual fuel cost for each system and the characteristic location was based on annual electricity and heating oil or LPG consumption, calculated on the energy analysis. The annual fuel consumption was multiplied by the forecast of the fuel price of the Cypriot energy system, and the annual fuel cost has been calculated. Moreover, the annual preventive maintenance costs were set equal to 2% and 4% for ground source heat pumps and boiler systems, respectively. Finally, the NPV value for each system was calculated for a 6% area discount rate. It is found that the ground source heat pump system presents the lower net present value when the building is located in the southern and midland areas of the island, where the conventional systems is most economically attractive. The one area, Saitas, is the only area that the ground source heat pump system was economic benefit than the other one. So to sum up, in this study, a holistic analysis of the installation of ground source heat pump system on single-family buildings in Cyprus is placed. It is found that the ground source heat pump system is beneficial with regards to the primary energy consumption, that it consumes up to 23.4% less primary energy than the conventional one. Besides, on the other hand, it is taken to, besides, the conventional systems is environmental friendly because the ground source heat pump systems emits up to 29 almost % more CO2 emissions. The results of the economic analysis indicate that ground source heat pump system is financially attractive for the coldest area of the island, while in the middle and hot climate areas, the conventional systems has lower net present value index. Sorry. Okay, I would like to thank you very much for your attention and apologize for my English. Thank you very much.
Thank you very much, Dr. Apostolos, once more. But just to make sure that your work has been done alone on your own, this is the paper being presented on this basis.
Yeah, it depends on a research project that we have in our university.
That's true. Well, thank you very much once more. If you have a question or two, yes, please.
Yes. Riyad Asaf, mechanical engineer, president-elect of Ashkari. Yes.
Sorry.
You have shown us some results. You have shown us some results based on a depth between 50 and 70 meters. On the other hand, you said you have, around 160, 160 points that you have encountered or you have in Cyprus. Do you have any data about more depths, or you don't have more depths? I mean the geothermal system.
Yeah.
Do you have results about going deeper,
No.
or this is your topography?
No, we have results. We do not have results for a deeper geothermal system. The common depth in Cyprus is about 100 to 150 meters. This is the depth.
Okay.
And this study,
because what you have shown is between 50 and 70, if I recall. This is it, between 50 and 70.
yeah.
So now you say that you have deeper. From deeper? Did you try something on deeper depth?
We have some results now for a multi-family building.
Yeah.
And there is the trend of the final results was the same. Almost the primary energy consumption is less than the conventional one. The CO2 emissions is more than the conventional one. And almost for the multi-family building, the conventional systems becomes more environmental, financial friendly.
Okay. Can you please clarify why CO2 emissions are more?
Yes.
Thank you.
Because Cyprus has a large emission factor. For electricity,
Cyprus, the emission factor is 0.8. It's for the highest of the European energy systems, and it depends on the fuel. Cyprus produced more than 85% of electricity using heavy oil, which have more emissions, and only 5% of the electricity comes from the renewable energy sources, mainly from two wind parks. We expect that based on the requirements of the European directives, in the near future, where renewable energy sources plants came into the electricity production system of Cyprus, this factor will be reduced, and this behavior will be changed. But from the literature, we have the same behavior in countries with high emission factor in electricity.
Because what I have understood is that using this system, geothermal system, the emissions are higher.
That's right. That's right. In this time, that's right.
Due to electric consumption.
Yeah.
But probably now Cyprus will enjoy producing natural gas, so this could help.
There is a discussion in order to introduce the natural gas in the electricity production sector, but we expect it to be after 2025. This is the target that we set to the Cypriot government last month. So we prefer the renewable energy sources. There is an obligation for 30% in the final energy production until 2020, and now is around 5 to 6%.
Well, in case no questions, thank you very much once more.
Thank you very much.
Our next speaker today is Mr. Sharvit Saif. Mr. Saif is a senior mechanical engineer at Dar al-Handasa, Shahar and Partners, Beirut. And his topic will be geothermal cooling application for fresh air treatment plant in Doha, Qatar. It's a case study. So please.
Okay. Good morning. Good morning. I'm here to present a case study that we made for geothermal investigation, to investigate the possibility of using geothermal energy in lowering the cooling demand of a fresh air treatment plant. The project, let's say, consisted of of 8 fresh air treatment plants, each supplying around 200 meter cube per second of fresh air. Doha is a hot and humid climate. The cooling demand for those plants represented a major part of the building or of the project cooling demands. So we tried to lower that cooling demand by investigating geothermal possibility of using geothermal cooling. We'll start by a brief introduction about the project. We'll talk about the basis of the design for that plant. We'll discuss the geo-exchange options, whether we use the 2 options that we have studied, the first one, which is the closed loop, the second one, which is the open loop. We'll go through, let's say, the methodology we use in evaluating both methods, and hopefully we'll share with you the conclusions we reached. As I've said, the project consists of 8 fresh air treatment plants supplying that project, and each has 200 meter cube per second air quantity. The available area, land area, that we have that's exploitable for geothermal exchange is the area beneath the parking of that project. So we are limited also in the area that we can use it for geo exchange. The outside design conditions that we used for that plant is 46 dry bulb. The wet bulb at that location is 30.5. We intend by this system to lower the outside air by 2 degrees, from 46 to 44. Why just 2 degrees? Because we are limited by the Doha ground temperature, and we are using water as a mean to exchange the heat from the air to the ground. The targeted, let's say, energy to be dissipated within the ground is 1400 kilowatt. We start by investigating, let's say, the temperature or the deep soil temperature. We checked published data by the state of Qatar, and the deep soil temperature tends to be around 26 degrees, close to the yearly average temperature at that location. The two options that we investigated are the ground vertical closed loop option, which is option 1, and the second option is the groundwater open loop. The first system consists of having water passing through a pre-cooling coil. It's used to lower the temperature from 46 to 44. The water is heated by the contact with air or through the coil. Heated water has to go down deep in the ground, exchange that heat with the ground, and cooled and back to the fresh air plant. For that, we'll be using boreholes, and we'll be having ground loops, so we'll have pipes that run deep in the soil. To identify the lengths of the pipes that need to be installed, we use the ASHRAE method for estimating the exchange between the pipe and the ground. It is function of several parameters. The first one is the ground temperature. The second one is the inlet and outlet desired water temperature. The third is the borehole thermal resistance. And what's more important is the annual heat pulse within the ground that is injected within the ground, the monthly heat pulse, and the daily heat pulse, which are RG, D, RGM, and the RGA. For the sake of this study, we considered that the ground temperature is 30 degrees. Why we took it, let's say, higher than 26, just to take into consideration any unforeseen conditions that may arise within the project. Since in our design, the ground temperature is 30, the water leaving from the ground temperature, we took it as 36. Why 36? To leave at least 6 degrees difference between the ground temperature and the leaving water from the ground to have an efficient heat exchange. The 36 degrees that enters through the air coil would return as 41 degrees heated by the air that's at 46 degrees. We ended by estimating the flow, and that flow was around 66.7 liters per second for that station. We started identifying the different parameters to identify the lengths of the geo exchange or lengths of the pipes. We started by identifying the diameter of the pipe in order to minimize, let's say, the friction loss within that pipe. We selected it to be 1 inch. And from the table provided by ASHRAE, we identified, let's say, the resistance through that bore, thermal resistance. We took, let's say, 3 cases, which is the daily heat pulse, and the time constant for it is in seconds. We took also which is tau 1, the monthly time constant for the monthly heat pulse, the tau 2, and tau f, which is for the yearly heat pulse. For those three taus or time constants allows us to identify the equivalent thermal resistance parameters. In order to identify those equivalent thermal resistance parameters, we need to identify the Fourier number, and that Fourier number is a function of those time constants. Once we identify the Fourier number, all you have to do is to use the graph provided by ASHRAE to identify the G factor. We have the G factor, then we can get the equivalent thermal resistance for the different heat pulses. Once we have those equivalent thermal resistance, we have to identify the net heat that's whether injected or taken from the ground throughout a year. Because if we're taking a case that we're injecting, let's say, or we're injecting heat within the ground during the summer, and we're taking, let's say, heat from the ground during the winter, then the yearly balance would be 0, and our system would be steady throughout the years. But if similar to our case, where we're just injecting heat during the summer, then after a certain period of time, let's say 10 or 15 years, the temperature of the ground will change, and the effectiveness of our system will decrease. So also we took that into account. We ended up by identifying the lengths needed to dissipate 1400 kilowatt within the ground, and it ended to be 44 kilometers. Based on a depth of 100 meters of bore, we needed 482 bores to cool that, to just dissipate 1400 kilowatt. So we started identifying, let's say, the cost versus the benefit. Another drawback is the low electricity rate in Qatar, which is 3 cents per kilowatt hour. So we ended identifying that even though we have a saving of a daily saving of 3100 kilowatt hour per day, the saving is reduced by the low electricity rate that's provided in that country. So in order to lower the cost, we went and investigated another groundwater or geo-exchange methodology, which consists on having a pumping well and an injection well. So we go down, we reach the aquifer, we pump, let's say, available water from that well. It could be, let's say, not really aquifer, it could be groundwater, dewatering, because the water level also at that location is high. And then use the heat in that water to cool that unit, or to cool that fresh air, and then re-inject it within the ground. We said that let's identify the quantity of water needed to dissipate that energy. Based on groundwater of 30 degrees and a water, let's say, temperature difference of 8 degrees, we did not intend to increase that temperature much more than, let's say, 38, just not to induce disturbance within the aquifer. We ended by requiring 42 liters per second of water. If we want to use the groundwater pumping, then we needed around 42 wells. If we want to go deep and reach the aquifer, then we can end it with 2 or 3 wells. Also, we checked the distance between the injection well and the pumping well, and we needed around a distance of around 60 meters between the production well and the injection well, to make sure that we don't have recirculation of the heat within the aquifer. We checked with the authorities that may give, let's say, give us the right to use that aquifer, and they denied that right. They did not accept that we use that system they fear that we will pollute the aquifer. So the final recommendation was the system was not economically feasible, and the only justification for implementing that system is the sustainability image of the project. So open well is not possible due to authorities' problem, while the closed loop system was possible, but it needed large investments. Those were mainly the findings. Yes. Thank you.
Thank you, Mr. Chairman. Time will be given for a couple of questions. Yes, please.
I have a question regarding
Please introduce yourself.
in the civil engineering department. The implementation of such a system for a large, relatively light structure may not be as economically interesting as, let's say, starting with a structure that would need to have piles anyway because of foundation support. And if I'm thinking of a high-rise or a building that anyway requires in this area relatively deep piles, maybe associating the geothermal, using geothermal piles, and that will defray some of the initial cost, and maybe that would be a more interesting proposition.
True.
And maybe you chose the wrong project to try to.
True. But in this, we investigated the thermal piles in another project. Still, we did not find a conclusion, but we can use it definitely because the piles are there. All you have to do is to run the pipes within the piles that are beneath the structure and identify it. Yes, it proved that for this kind of project it was not that feasible.
I have another question.
Yeah.
Does Qatar have currently a policy to encourage energy efficient buildings, or they will keep subsidizing the electricity cost?
The problem is not they keep subsidizing the electricity cost, but the problem, the argument with them is to say that if you use less energy, then you burn less energy, you burn less fuel. If you burn less fuel, then you can sell more fuel to outside. Because now they have a problem, which is they have around 7 or 8% of the produced energy they have is locally consumed. And with the projection for the next 15 years, it's expected to rise up to 20% or 25%. And majority of that energy is taken by the cooling sector, because that's the thing. So even though the rates are low, from a client point of view, he's not interested, but from a country point of view, it's very important. And they have something called QSAS, which is sustainability requirement. Assessment system. So they are encouraging sustainability measures.
Other questions? Well, I take this opportunity to thank you again.
Thank you.
Is Mr. Prasad here? The third speaker? Mr. Prasad? Apparently I don't have his presentation, so I was assuming that he would come with it, unless he did not show up for the... Okay. So you need a chair?
No chair.
All right, thank you. And his name is not here?
His name is Tanmay Jain and I'm Harish Mahadas.
You're Jain Tanmay?
Tanmay Jain, he's going to present the paper. I'm just going to assist him.
Okay, fine. Well, let me welcome Mr. Jain Tanmay, and I apologize for calling you from previous presentation. Let me introduce again Mr. Jain. He is pursuing his bachelor in technical in mechanical engineering at IIT Roorkee. His areas of interest include thermodynamics, powertrain systems in automobiles. Currently, he's working on alternative HVAC systems, earthen HVAC systems in particular. He has been involved in a project under the
AGs of mechanical department, which deals with design and fabrication of an all-terrain vehicle. His presentation is titled also the Earthen HVAC System. Please go ahead.
Good morning, everyone. Myself, Tanmay Jain, and I'm a Madashu. He's also an undergrad student in the department of IIT Roorkee. As mentioned, we are here to present our idea on earthen HVAC system. Okay. So this is the layout that will be following in the entire presentation. So first, we will consider the discussion of the problem. There is a whole world, the whole world is facing a problem that is popularly known as energy crisis. So we will discuss the problem in developing countries like India and China, and also in South American regions. Then we will present and propose our idea, and we'll discuss that what made us think about that, and we'll discuss the stages in which we modified our idea into the final design. Then we will discuss the impact and scale of our idea, what are its consequences, what are the drawbacks, and what are the benefits, and then we will see the environmental impact, have an insight into that, and conclude it. So, the energy crisis that is going in the world. So first of all, we will look into the South American region. That is, you can see this graph. It is a graph of the energy consumed in different appliances, in air conditioning, in refrigerator, in space heating, and etc. This is for South American region. So we can clearly see that in 2009, more than 20% of the electricity was consumed in air conditioning. And if we compare it to the 1993 graph and 2009 graph, it is seen that the amount of energy consumed in air conditioning is increasing. And this trend is also increasing right now. And so, of course, it has grown from about 20% electrical consumption to more than 20%, much more than 20% consumption. So, let's see the case of developing countries, India and China. As you can see in the graph, this red line represents the graph of the air conditioners per 100 urban areas in China. That is, the trend is seen to be increasing. Until date, it is increasing. Same goes for India. We will discuss in the next slide about the Indian case. And the demand of air conditioners in the developing countries is growing day by day. So if the demand of air conditioners is growing day by day, as goes the demand of energy consumption, electrical energy consumption. And hence, there is a consequence of global warming because of the production of electricity that we do. So, next slide. Now, this is the situation in India. In India, we have taken two places in consideration, that is Mumbai and New Delhi. Why we have taken these places into consideration? So, let me give a brief idea on these two places. First of all, Mumbai. Mumbai is a coastal region in which the climate is hot and humid. So, we have taken this into consideration. And New Delhi. New Delhi is a place where both the seasons are at extreme level. In winters there is too much cold, and in summer the weather is too much hot. So we have taken this into consideration. Now let's see one by one. First we will see of Mumbai. As you can see, these are the residential load curves for the Mumbai on a 24-hour basis. So the blue line represents the residential load curve in summers, and the red line represents the residential load curve in winters. So as you can see, the Mumbai, it starts around somewhere 2300 megawatt in summers, and it has a peak at around 27 or 2800 megawatt. But in Delhi, it is opposite. Means it's very high. As I mentioned, that in summers it's too hot in Delhi because of its arid climate. So it starts around 3600 megawatt and has a peak at around 4200 megawatt. Now, in Mumbai, as I said, that the difference in the temperatures during winter and summers are not so magnificent. So there's only 700 megawatt difference during the peak time of energy consumption due to air conditioning. But in Delhi, there's a lot of difference because in extreme cold and extreme hot. So it is 1600 megawatt. Now, this difference that is coming, it is purely due to air conditioning. It is related to air conditioning units only. But the amount of air conditioning units that are consumed, the deflection is due to that. So basically, what is our idea? Every one of us here know that the earthen material was used, and nowadays also it is being used to cool water. The earthen material is used to cool water through evaporative cooling. So we have exploited this property and used in our system so that we can provide a renewable source of air conditioning, so without much power. Next. So details. So first of all, now from here we'll visit that what we first thought and how we led to the modifications in the designs. So first of all, we thought that we will consider a box type heat exchanger, that as you can see in this. In this, there is a composite wall. This is earthen material and inside are metal walls. So in the composite wall, the water is filled up and there is a double pass air. Air is passed through this and it completes the one round rotation and goes into the cooling space. Now the question arises why we are giving a double pass for the air. Why are we giving the air a long path to enter into the space? So these are the basic principles of heat transfer, which says that we should increase the duration of heat transfer and we should increase the surface area of heat transfer. That's why we are presenting a double pass. Now what will happen for this water, the earthen material will cool the water inside the composite wall, which in turn will cool the air that is passing through it, and this air will be cooled. Now for evaporation of water, there is one more thing that need to be considered. That is, one is for the evaporation, the humidity should be low and temperature must be high. So this is the drawback of a system. But the bright side is that it is very efficient for the hot and arid climates. And mostly in Middle East and the native place where I came from, India, there are mainly the regions which are having hot temperature and moderate humidity. So it is good in that. So our basic aim is to do evaporation of this water. So how could we achieve that? We could achieve by the air that is flowing through it, that is natural convection, and the water will be evaporated and further the consequences will be held. Now, but there is a problem with this design, and it is sharp edges. During sharp edges, what will happen? It will obstruct the airflow and hence the warp formation will occur and hence the moisture will not be dissipated. So we then shifted to another design, that is cylindrical design. It is the same design but only cylindrical in shape. Here also you can see that this is the earthen material, this is the composite wall, and these are the two metal walls. So instead of using one single cylinder, we scale down the model and use multiple cylinders. So we have two options in our hand. One is inline grid and one is staggered grid. So as you can see from the picture, that inline grid is the straight arrangement of the straight array of the cylinders, and in staggered grid, each cylinder is in between the preceding column two cylinders. So this is the staggered. The problem with the inline grid is that this is the starting point. After successive rows, the warp formation will take place and the heat dissipation would not be good. So that's why we opted for the staggered grid. And yeah, next slide. So this is the staggered model. You can see the top view, isometric view, and the front view. This is supported by natural convection, and the air will flow through the blowers that we have provided, and the mechanism is same as we have mentioned in the cubicle system. Only the change is that the design is cylindrical. So this is, you can have a better look at our design. This is, as I said, earthen material, composite wall in which the water will be filled up. There are two metal plates. In this is a double pass. The air will flow from here and enter the cooling space, and through the ducting system, we will provide the fresh air to the space where we need cooled air. So the problem with the staggered configuration was that it depends on the direction of wind, in which direction the wind is flowing. So to eliminate that problem, we have gone a further step. We have stepped ahead, that we have considered a symmetric circular grid. In this, it will be independent of the direction of wind, and it will not depend whether the successive layer warp formation will take place or not. So basically our idea was on earthen cooling. So we have done experiments on earthen pot, and we have checked our results with various research papers also. So the main readings or main key points of the experiment that we got were, first of all, the highest temperature depression in the water was in the peak time, that is 2 p.m. to 4 p.m. when there is maximum temperature. And also the humidity should be low or moderate, and the temperature should be high. These were the conditions that needs to be met. And the ideal temperature that is achieved by air condition is supposed to be 24 degrees Celsius, and it can be achieved through this system. These are some energy calculations we have done through mathematical calculations, and we arrived at the result that it reduced 25 to 30% of power consumption that is done by the natural convection system. Also, this system can be supported or complemented by the use of different host supporting systems like air indoor quality monitoring system, CO2 monitoring system, and various other systems. But this is not an additional requirement. These are conventionally used in the conventional air conditions. Now, how can it be used? It can be used directly over the households or directly over the rooftops of the high-rise buildings, and then the complete grid can be kept in the rooftop of the buildings, and through duct system we can provide the air into the cool spaces. Who will be the customers of this system? The people who have a huge spaces but want moderate cooling can use this system, because it can work upon the customer requirements. If you want more air, the conditions and parameters can be arranged. They are flexible, so you can arrange according to your cooling requirements, according to your space, and it is purely dependent on customer requirements. If your requirement is something, it is flexible enough to to satisfy your requirement. High-rise buildings, air condition manufacturers, and industries. Yeah. So basically, at the end, it is a greener technology. It uses greener material, that is earthen material, and it does not provide only little pollution, not much. And the basic thing is, it is an idea. So a lot of research work has to be done. We are doing actually on the complete research of this. So this is basically an idea that we have proposed, and thank you for providing such a platform to present our idea.
Thank you, Mr. Jain. Any questions?
Well, I have one. Do you patent such thing at home?
So actually, for patent, a prototype has to be made. So we are building the prototype, and then we will go for the patent. Because this is a new technology, the procedure is going. So I said at the end that the research work is still going on, and the major drawbacks, if it came that okay, this is not proper, this is to be changed, so we will do this, and the process is in progress. We are going for it. Yes,
Yes, Riyad Asaf, mechanical engineer. Can you give us, please, an idea about the water consumption?
Sorry, sir?
About the water consumption, because you are using water.
So actually, we will be, if required, if the water level comes down after a minimum level, there will be a drip system that will refill the water. That's what you asked, right? How will I control the water?
The consumption, how many liters per hour, per day? Because in desert cooling,
yes.
Desert cooling, okay, the water vanishes because we throw it in the air. So there is a consumption of water.
How much water that
Yes.
it's...
An idea about
Make up. You lose water.
Table.
Depending on the cooling.
This is mass of operation. But the initial mass of the water we have taken is roughly around 4.6.
So basically we have started with 4.69 kg, and when we conducted for 60 hours the experiment, it came out to that only 31% of the mass was evaporated was this. 31% of the water that were put, it evaporated. So according to our needs, we can, there will be inbuilt drip system. So if there is necessary that water has come out a minimum level, we can control that drip system so that the water fills to the dip, to the brim, and the evaporation would further carry on. Because after some level of water, if the minimum level, if the water passed through the minimum level, so the evaporation would not be so efficient. So the system would not be so efficient. So there will be a minimum level, and after that, if the water falls below that minimum level, then there will be a drip system that is self-monitored, and it will fill the water above the minimum requirement level.
Okay. You said also that we can use a recycled water or grey water. Grey water. Wastewater. Okay. Did you make any experiments to see to define the TDS level of this water that can be used? Because we cannot use directly the wastewater. It should be treated.
It should be treated, but sir, this is just a proposal that we are giving. We have not actually done in the prototype, but we have used distilled water for the purpose of evaporation, and we are still working on how to use wastewater and what TDS we need in that, so that it can be used and what kind of treatment should be taken.
Because up to our knowledge, the consumption of water is high in desert cooling.
Well, yes,
so we need big tanks of water to be used in desert cooling. So what you are gaining in energy, you are losing in water if it is not recycled water.
It's the same power consumption. Desert cooler and evaporator, the same.
Yes, I'm saying we are using water, so we are using a very precious natural resource.
This system is very good in a dry area, and,
yes, only in dry
and the water is available. Like in Sudan, we are coming from Sudan. There is a Nile River, and the water is cheap. So this system very efficient.
When you are close to the Nile, but when
yes,
you are far to the Nile, it's not.
Yeah, no, sure. Like Lebanon, Jordan, there is no water.
Okay, so no further questions. Once more, I'd like to thank the two gentlemen here, and thank you for attending this morning technical session. I'll see you in our you may join up. Yes, there will be an ongoing presentation now.
No, but then lunch.
Lunch now.
Much
And lunch.
better quality today.
Okay, lunch will be served up.